Morning, Physics 30. Hope you guys are having a good day so far. So I've been told to work from home for the next couple days. So welcome to my office. Please excuse the lighting in here. It's not that great. So I may look a little bit bright or what have you. Oh, hello, and there's my dog. Freya is very happy that I am working from home. I don't know if you guys can see her snoot. There we go. She's enjoying the fact that I'm home all day. Yes, I know. Life is exciting when you're a puppy. Yes, I know, Freya. Yes, we're filming. Can I please do my physics lesson? Apparently, Freya says no physics lessons. She says that I must be paying full attention to her, apparently. Right? Right, Freya? Yes. It's a good thing she's cute, right? Okay, so our topic for today, as you can see by the background, is Lenz's law. And so key piece with Lenz's law, ladies and gentlemen, is that it is based on the concept of, where is the pin feature? Why is it not working? Because it's not plugged in. You know, it might make a difference if I want this thing to work if I plug it in, huh? There we go. Okay, now we're working. So the key piece with electromagnetic induction, ladies and gentlemen, this is how we make electricity, by moving a conducting wire through a magnetic field. It's the whole principle behind AC generators, where we get all of our power from inside, from our plugins, okay? From a little crank generator that you have in your car and a flashlight, or a generator that runs in your motorhome or camper trailer. Okay, so ladies and gentlemen, let's look at a basic review diagram. We're going to have a magnetic field that is going to go into the plane of the page here. And if we are going to move a wire through this page, we are going to get let's try this again. Put a wire in this field that has electricity moving through it. It's going to experience a magnetic force. So here is our wire in the field. Okay, we're going to assume it's actually perpendicular to the field. And if we are going to put some electrons to run through this, so if we have a current running through this particular wire, we are then going to result in a magnetic force being experienced. Now, how do I know my magnetic force is going to go this way? Left hand roll. Okay, so you're going to put your thumb in the direction of the current, and then your fingers in the direction of the magnetic field, which are these red lines here as your B perpendicular. So the force is going to be going the direction of your palm, which is going to be going that way. Okay, so that is our review. But now we're going to be looking at the opposite concept, where we are going to be taking a wire that doesn't actively have electrons moving through it at this point, and then we are going to be providing an external force to force that conductor to move through that field. That movement of that conductor through the field is going to cause electrons to flow. So let's draw our field again. So let's draw our field with red X's. We're going to have our field going into the plane of the page again. Okay, and now we're going to draw our wire. There's our conducting wire. Now, this time, I'm going to apply an external velocity to this wire. I'm going to take this wire, and I am going to move it this way. It doesn't have a conductor, a flow of electrons moving through it. We're going to add velocity, and we're going to move it that way. Okay, let's finish some labeling here. Let's give this guy, for your notes, that is your B perpendicular, these X's here. Now, when we're going to move this conducting wire through there, we're going to wind up with electrons that are going to be flowing this way. Now, how do we know electrons are going to flow in that way to begin with? Well, that is what has to do with Lenz's law. Okay? So, ladies and gentlemen, for your notes, give this guy a star. Okay? So, your conductor forced to move through a magnetic field can and will produce an electric current through that conductor. Okay. Now, like with any device, we can take these electrons and that are going to flow through this conductor, and we're going to make these electrons, we're going to make them do some work for us. We're going to make them power light bulbs. We're going to make these electrons power your cell phones. We're going to make them power our computers and all the bits we're depending on for education these days, just technology. So, the term where we're going to be forcing electrons to move through a conductor by moving that through a magnetic field is called electromagnetic induction, which was first discovered by Faraday. And it's going to create an induced current. So a current that we are forcing to flow through this by moving this conductor through a magnetic field. Okay. So the very, very, very important part, ladies and gentlemen, that I want you to put a really, really big star beside is Lenz's law. Now, Lenz's law, this is probably the most important piece of this set of notes here, ladies and gentlemen. The induced current is going to flow in a direction that is going to oppose the direction of the external force or the motion. So if you are going to be moving a wire this way inside of a magnetic field, it means that the magnetic force is going to be in opposite direction to the motion. Okay, so that is what we're going to happen. That's happening here. Okay, so if the velocity is going one way, the magnetic force is going to go the other. And we're going to be using this in conjunction with our hand rules. Jazz hands. Woo! Okay. So the two big ones, because we're dealing with flowing electrons for the most part, we're going to be using our left hands. Okay. So we're going to scroll down here. All right. So let's look at our first example. Our first example is we have a length of wire, and this entire length of wire is going to be flowing through a magnetic field. So when you see these X's here, these are this is your magnetic field going into the plane of the page. Now, with our velocity of this wire here, it's being moved this way. So if it is being moved that way, that means that your magnetic force is going to be going that way. So for this one, because we have a conductor or conducting material moving through this field, we're going to need to use our third hand rule. Okay, so you're going to take your left hand. We know our force is going opposite in the direction of that velocity because of Lenz's law. So I'm going to take my palm, which is my force, and the force is going to be going in the same direction of that. That's going up this way. I'm going to turn my hand this way so that my fingers are going to be going into the plane of that page, which is where my field is going. So your field goes this way. My thumb is going to be where the electrons are going. Okay, so my electrons are going to be flowing this way through that wire. So let's think for a moment. A negative end of the wire is going to be what? The source of electrons. Absolutely. So, oops, that's not where I write. I write here. Okay, so my electrons are going to be going that way, which means that's going to be my negative end of the wire, and that this is going to be my positive end. Sounds good? Okie dokie. All right, our next example, let's erase this random FM here. is going to be about a solenoid. Now, because we're going to be dealing with a solenoid, ladies and gentlemen, we're going to need to use our second hand rule. Okay, now we're once again dealing with flow of electrons, so left hand, and we have our lovely magnet here, and we are trying to determine what direction we are going to move this magnet in order to get the current shown in the diagram. So if we take this magnet and we move it through this solenoid, we need to determine or this way through the solenoid to get this current. So let's take our second hand rule, and we're going to get our fingers pointing into the direction of that electric current. So I'm going to put my fingers this way, so because when you look at the arrows, they're pointing down. So I want my fingers to be pointing in that direction of that electric current. So what this means is that my thumb is going to be pointing in the direction of the north pole of the magnet. So that's going to be north, and that is going to be south. Now, because this north pole is of the solenoid here is going to be repelling the north pole, that means the force magnetic that they're going to be experiencing is going to be going to the left in this diagram. Now, we need to think for a moment. Lenz's law said that the magnetic force is going to be opposite to the velocity. So what velocity do we need to move? To the right. So we're going to have our velocity going to the right here in order for us to get that particular current. Isn't that fun? Yeah, it's fun. Hand rules, they're awesome. Okay. Oh, sorry. My dog's barking at the garbage truck or something. Scary garbage truck. To a dog, anyway. All right. So our next question here is predict the direction of the induced current in the solenoid. So here's our solenoid. Our motion is going upwards here. So if that is the case, that would mean the electric force is going to be going this way. Magnetic force, excuse me. Okay. So what that means, there we go. If that's going to be the case, this is our magnets that's being moved this way. Okay, it's all one magnet flying through there. So if our force is going to be going this way, what do we do next, ladies and gentlemen? Well, our north pole is this way. So if our north pole is this way here, well, guess what? Our electrons are going to be going this way. Okay? Okay, because our thumb is going to be pointing in the direction of our north pole. Okay, so our electrons, I can't write on that piece. There we go. So our electrons are going to be flowing this way through our wire. Okay, so ladies and gentlemen, that is Lenz's law. Short lesson today. So you've got some practice problems there to do, and then you guys have a couple of other practice problems which you can have a go at here in your notes. Okay, so give these a try, and if you guys have any questions, fire me an email or comment on Google Classroom, and have a good day. We will talk to you later. All right, no fires, injuries, or explosions, ladies and gentlemen, and catch you on the flip side.